remember from chapter 12 that water can undergo an acid catalyzed addition to an alkene or an alkyne to produce an alcohol or a ketone, respectively, depending on whether you're starting with an alkene or alkyne. The first step of that particular mechanism, the proton adds to one of the alkene or alkyne carbons to produce the more stable carbocation intermediate, right, with that Markovnikov regiochemistry. Then the water attacks the carbocation in a coordination step. Now, one drawback to these reactions is that carbocation rearrangements are possible. And that's what you see here in this equation, right, is that we end up with a carbocation rearrangement. Now, carbocation rearrangements in and of themselves aren't bad. We just have to remember that they happen. So if you're trying to make this, then this is a great starting product. But if you're trying to get the OH to add to across the double bond, then this is not a great starting product. There is another way to add a functional group to a molecule, and that's the Oxymercuration Reduction, which is also called the Oxymercuration Demarcation. That's an older term, to add water across a double bond. Okay. Now, here's an example of that particular reaction. What you notice here is the alkene is treated with mercury 2 acetate. And so that's what this is here. So that's mercury 2 acetate. Okay. And this is in a water tetrahydrofuran, which is a THF solution. So that's tetrahydrofuran, and that's just a common solvent. Okay. That's followed by the reduction. So the function of the sodium borohydride here is a reduction reaction. Okay. So this is a sequential reaction. So you do step 1. You work it up, and then you'll go through and do step 2. Now, there are 2 kind of big things that you see here. One is the product of this reaction is the one expected from the Markovnikov addition of water. Okay, and so that's what we can see there. And so what that means is that the OH group forms a bond to the carbon that can better stabilize the formal charge or the positive charge. And then the other thing, and this is the big thing that makes this advantageous, is that carbocation rearrangement does not take place. Okay, and so we don't have a carbocation rearrangement that we really have to worry about here. Now, to better understand this, let's look at the mechanism. So when we look at this mechanism, the first thing that you need to be able to do is draw the mercury 2 acetate, which is, if you remember from the previous slide, HgOAc2. Okay, and so what this looks like right is this guy right here. Okay, this oxygen, all our oxygens, I'm gonna go ahead and put the electrons on them. Okay, and then let's look at our alkene here. Okay, now the first step is a concerted step. It means it all happens at once, and what we see happening is the double bond, the electrons here, will come up and they'll attack that mercury. When that happens, these electrons come down here. Now, they're in proximity, so this is happening at the same time. And then these electrons, that bond breaks, and they go there on the oxygen. Okay, now, this is an electrophilic addition step. Okay. And what happens is that we form a ring with mercury. So when we look at this, the complex looks like that. And the mercury has a positive charge on it. Okay. Now, this is called a Mercurinium Ion Intermediate. It's such a hard word for me to say, so I really have to think when I pronounce it, right? But so we get this intermediate, and one of the things to be aware of is that this side of the ring here bears a larger partial positive charge than this side of the ring there. Now, if you were thinking, hey, we have seen this before, you would be right. We saw this in protonated epoxides in Chapter 10, and then in bromonium ions kind of earlier in this chapter. So the Mercurian ion has this three-membered ring, and it's stabilized when the heteroatom shares some of its positive charge with the two attached carbons. And so the carbon can better handle the positive charge, picks up a greater share of the positive charge from the heteroatom. So the secondary carbon of the ring can better handle that positive charge than the primary carbon can. Okay. And that has to do with those R groups. Now, okay, the next step is an SN2 step with water. All right, where these electrons are going to come in and attack this carbon because it's more partially positive. When it does that, it's going to open the ring here. The ring opens up and we kind of visualize that flopping over, and we end up with this intermediate. We've got two electrons and a positive charge here. Okay. Now at this stage, we're going to have a proton transfer. Right, where water comes in and the water comes here and steals, the electrons here steal this proton, and these electrons go back on the oxygen. Now, when that occurs, this is the intermediate that we get. And then we're going to add sodium borohydride here. So that's that second step. And that's going to reduce that carbon atom and replace the Hg group with a proton. And you can just show this. If I asked you to show the mechanism on exam, you can just draw the three arrows and say add NaBH4. And then that's our product that we get there. So this mechanism shows why rearrangements tend not to take place in oxymercuration reductions versus that acid-catalyzed hydration. In the acid-catalyzed hydration of an alkene, a full positive charge develops on the carbon in the carbocation intermediate. And here we only get that partial positive charge. And so with a smaller concentration of the partial positive charge, a rearrangement wouldn't really help with stability. So we're not going to increase the stability of a carbocation here. So the fact that we don't have a full partial charge is the reason that we don't end up with a carbocation rearrangement. Now, even though this oxymercuration takes place with an anti-addition, which is what we're kind of looking at here, the stereochemistry of the carbon atom bonded to mercury is scrambled during the reduction step. So when that happens, the net addition of water occurs to give both the syn and the anti-addition products here. So we get both syn and anti, okay? And so that means we're going to end up kind of with those two enantiomers you can see there. So the sodium borohydride just scrambles the stereochemistry. Now, maybe the burning question in your heart is, hey, we did this with alkenes, and I know that the other reaction also works with alkynes. Does this work with alkynes? And the answer to that is yes, you would be correct if you guessed yes. So alkynes also can undergo this Markovnikov addition of water by oxymercuration. However, just like we saw with that acid catalyzed hydration of an alkyne, an unstable enol is initially produced. And so you get a subsequent tautomerization that converts the enol into the more stable keto form. And you can see that here. So that unstable enol is produced initially. So tautomerization from that enol to keto form occurs. Okay, and so we end up here. So if we add water across a double bond using the mercury acetate, we end up with an alcohol functional group. If we do this with a triple bond, we initially get an alcohol, but it almost immediately rearranges, and we end up with a ketone functional group. And so that's what we see there. Now, one of the things to notice here is the reaction conditions are different. Right? These guys are different, and it falls right in here. I want you to notice instead of water and THF, you just have water, and then you have acetic acid. You don't have a reduction with sodium borohydride to remove the mercury substituent. Here, right, the merconium ion, and actually I forgot to flip over, right? Here, the Mercurinium Ion Intermediate is going to open to produce this mercuric enol, and then afterwards it's going to tautomerize to a mercuric ketone. Okay, so this is really where we see the enol to keto tautomerization, and then water just hydrolyzes it to produce the enol shown here, which of course was shown on the previous page. So we end up really with two keto enol tautomerizations. The first one is a mercuric enol to ketone, and then we get the other enol to ketone there. Now, mercury 2 acetate is not the only source of mercury used for these oxymercuration reactions. Here are two other examples that we have. You can see here that you can use water and mercury chloride, and that's a mercury 2 catalyst. And then you can see here water and mercury sulfate with sulfuric acid and acetic acid. And both of these, again, produce ketones. Now, internal alkenes can also be converted to ketones. We've been looking to external alkenes here, terminal alkenes. But internal alkenes can also be converted to ketones. Now, the problem is that unless the alkyne is symmetric, you get a mixture of isomeric ketones being produced. So you'll get a mixture here. We're going to digress for just a little bit, but heptane 2-one, which is shown here, is believed to be used as an anesthetic by honeybees when they bite small insects and larvae that enter the hive. It's also responsible for the odor of gorgonzola cheese. So if you like gorgonzola cheese, that's the odor that you're smelling, which is kind of interesting. Now, all the oxymercuration reactions we've looked at so far involve the addition of water across a carbon-carbon double bond or a carbon-carbon triple bond. If an alcohol is used as a solvent instead, like what we see here, here's the alcohol being used as the solvent, then the ROH adds instead, and the product is an ether. So one of the things that you're going to see all the way through organic chemistry is if we see water reacting in one way, then we can almost immediately apply that to an alcohol being able to react the same way because of the structure of water, right? Versus, say, the structure of an alcohol, where we've just replaced one of the H's with some sort of R group. So this is called an Alkoxy Mercuration Reduction reaction. And of course, we produce an ether here. So let's work on a problem, okay? This problem says, draw the complete detailed mechanism for the alkoxy mercuration part of this reaction and predict the major product. So let's look at this. Here's some questions that we need to ask ourselves. When the alkene reacts with mercury acetate, what species is electron rich and what species is electron poor? And then is there a lone pair on the electron poor atom? So when we think about this and that first question, which I left myself no room, and I probably didn't leave you any room, so I apologize. So I'm going to come down here. I'm going to say, okay, so when we look at this guy for the mechanism, right? And we are going to draw out that mercury acetate. Now, I drew it out one way previously, and I'm going to show you here another way that you'll see sometimes is it drawn out like this. You can choose either way on a test, but I want to make sure you recognize both ways. And so we see the mercury here, okay? And so when we identify this and start looking, this carbon-carbon bond of the alkene is electron rich. And the mercury atom here is electron poor. So when we start this mechanism, we're going to draw a curved arrow from the carbon-carbon bond to mercury to represent the formation of one of the carbon-mercury bonds. And then when that happens, so we start here in the middle, and we draw up here, right? These electrons then come down to here, and then one of those acetates pops off, okay? And when that occurs, we form our triangular structure. Okay. And so now we have our intermediates. And so the next question you ask yourself is what nucleophile reacts with the intermediate and how is the regiochemistry of that step determined? So when we look at this, and we look up there, we see that this is in ethanol, right? So we look here at the top, it's in ethanol and THF. THF is just a solvent, so we're going to ignore that right now. But what we have here is ethanol instead of water. So ethanol is going to be our nucleophile. So I'm going to go ahead and draw an ethanol. There's a couple different ways you can draw this in. You can draw CH3, CH2OH. You can also abbreviate it as ETOH, ethanol OH. I don't care which one you do. I want you to be able to recognize both, right? And so when this occurs, you have to ask yourself, which carbon, when we talk about the regioselectivity here, what we mean is which carbon's attacked. And we know there's a bigger partial positive charge here than at that carbon. So those electrons are going to come up and they're going to attack that carbon there. When they attack that carbon there, these electrons, and I should have started in the middle, but that large partial positive bumped me over. So those electrons are going to come up and be on the mercury. I'm going to draw that arrow just a little better down to that mercury. So it's on the mercury there. And I'm drawing my next structure here. Right, and there we go. And I'm just double checking that I haven't lost any bonds. Okay, so we've got this structure here, and then we're going to see a proton transfer. The ethanol again is going to do that. So it's going to come over here. It's going to grab that proton. Those electrons are going to go there, and then we get right there. Okay. Now, the next question we ask ourselves is, are we going to have a carbocation rearrangement? The answer is no, because this is the Oxymercuration reaction, right? We've got those partial positive charges, so we're not going to see any rearrangement here. And so then the next question you ask yourself is, okay, we've made it through the first reaction. Now we're going to add NaBH4, and what's the role of that? Well, the role of this is that the NaBH4 replaces the mercury containing substituent with a hydrogen. That's all that happens. And so now right, and you can draw this guy as an answer, and that's totally fine. You can also, and I don't generally love this, you can also draw that H bond out if you want. That's something you're going to see in your book, right? And I don't really care if you draw the H or you don't draw the H. Honestly, I would probably answer like this, because that I just don't love drawing the hydrogen there. But if you are more comfortable drawing the hydrogen, then you're more than welcome to do that. So this for us concludes the oxymercuration reactions that we see. In the next screencast, we're going to look at a hydroboration oxidation reaction.